Hi, year 12s, Miss Corrigan here. Possibly wondering why the lighting is off. I recorded this fully through and I did it wrong. So let's hope we can get through this without any hiccups, but sure be grand. Anyway, we've been meaning to make loads of videos, but I suppose the most important thing to us was that you do the intertopic test first. You kind of go over any mistakes you made, and then even after the revising, any clarifications or any sort of conceptions you wanted addressed, we could make a video on it. And we've come to that time now, which is great. So I want to thank all 8 of you for filling in the survey earlier. Really, really important stuff. Those of you that haven't, please go and do it. It was compulsory. It really helps us help you. And we do need to see a bit more engagement. So if you haven't done it, pause this video, go and do it, and then come back and we can continue because it is really important. Saying that, let's do it properly this time. On my end, it was very clear all of you wanted to go over halogenalkanes. So it was a good insight for me because again, it was my understanding that we'd covered it. And I suppose I was under the assumption that we were quite comfortable. But seeing this right here tells me that no, we're not, and yes, we should go through it, which is great. So let's go through it. But before I do, actually, I can see here that there's actually no sort of specificities. So if I was going to hunch, I would say that people might be struggling with free radical substitution. Coupled with that is the ozone depletion. Maybe people are still struggling with that. The nucleophilic substitution reactions are always a hoot, and the elimination reactions as well. But I suppose I'd like to kind of step back a little bit, and I will do videos on those. Even in the introduction and sort of like not really the basics, but the intro, students still struggle with concepts like why do certain halogenalkanes have more reactivity than others. So that's a really important concept that students still sort of struggle with a little bit. So what I'd like to do is I'd like to make a kind of a general introduction video where we kind of talk about just the sort of the physical properties and just even the nomenclature, etc. Kind of get through that, and then the other videos will be more along the mechanism side. So moving on, what are we doing today? So we want to go through what are halogenalkanes. We're going to classify them into the kind of the physical property realm. We're going to look at the bonding and the reactions, and then at the very, very end, there's some really nice sort of long MCQs that you can try after, and it'll really kind of help you get to grips. Hopefully it'll be a good assessment tool to kind of tell you how well you're grasping the concept. So starting off, when we always start off a new topic, I want to talk about the spec. So to be honest, we're doing probably 85% of what's on here. So we're going to talk about halogenalkanes containing polar bonds. We're going to talk about halogenalkanes undergoing substitute reactions with these nucleophiles. Now again, the actual detailed mechanisms will be done in separate videos, but we will be talking about the nucleophiles and how they might kind of start the reaction. So repeating myself again, students should be able to outline nucleophilic substitution reaction mechanisms in a separate video. The next line here, explain why the carbon-halogen bond enthalpy influences the rate of reaction, is probably the main reason why I'm doing this video. That this is where I do see a lot of confusion with enthalpy, but again, we will address that when we get to it. Over here then we have like carrying out test tube hydrolysis. So if you remember sort of the halides, kind of test tube reactions, we had our iodide, we had our bromide and our chloride. They kind of form precipitants under certain conditions, so we'll look into that too. Okay, now this is I think where I went wrong the last time. So if I'm right, I go here, I go share screen. Now she's up in diesel. Grand. All right, good to know where that mistake was made. Now, so what are halogenalkanes, first of all? So they are surely represented by this R and X, but what do these actually mean? What does the R represent and what does the X represent? Do you remember? And if you remember, write it down. Pause the video. See if you can remember. What does the R and the X represent? have a think. So if you remember, the R represents what we would call, I suppose, the carbon end of things. It represents our alkyl groups. And our alkyl groups would be our methyls, ethyls, propyls, butyls. That's our alkyl groups, kind of our carbon containing area. And then our X then is our halogen. So our halogens are our group 7s, as we can see down here. Quite slow writing this down. So thinking about how this is represented and thinking about the types of different formulas we have to know, can we think of what is the general formula of a halogenalkane? What is the general formula? What do I mean when I ask you what is the general formula? Have a think. Loads of different formulas out there. We've got structural, skeletal, molecular. I'm asking what the generic or general formula is for this. Do you remember? I'll give you a hint. C, N, H, 2N. Are we done? No. Plus 1. So if you said plus 2, you're referring to an alkane. We're looking at a halogenalkane. So the halogen is going to replace the hydrogen off of that alkane pretty much, and it's going to become CnH2n plus 1. And of course, throw our old X there to indicate our halogen. So when we talk about halogenalkanes, we first of all we describe them as saturated. And what do we mean when we mean saturated? Comes up in definitions all the time. What is a saturated compound? It's one that contains single bonds only. If you don't push that only down, you don't get the mark. So saturated compounds is one where it would contain single bonds only. An unsaturated compound, on the other hand, would contain double or triple bonds. Saturated, single bonds only. Very important. So now again, it contains at least one carbon, halogen. So the alkyl group, or the carbon kind of area there, the hydrocarbon area there, I should say, contains at least one halogen. So if we look here, if we scroll down here, we see we've got a carbon and at least one of these halogens, so fluorine, chlorine, bromine, iodine. So it could contain all of them. It would still be halogen. If it was a carbon and it had all of them, it would be halogen, or it could have one of them, it's a halogen. So it contains at least one of these bad boys over here. So before I kind of brush on a little bit, I want to take a little bit look. I know you're kind of sick of seeing it now, but I do want us to sort of revise nomenclature a little bit. And I'm going to give you a quick old problem, and I want you to tell me what it is. So if I just, oh, Joe, I'm actually going to change the screen. Hold on a second now. Do not want to make that mistake again. Bear with me now, folks. So I can just do, yeah, I got it. Right. Back here, there we go. So I'm going to give us a problem. I'm going to give you the name of an organic compound, and I want you to figure out how you're going to draw it. Ugh. Sorry, I'm just very paranoid that I haven't got this recording. I do, be confident. I have it. Right. So again, if you're going to draw this out, how would I draw it out? You might have got a glimpse of it, but sure, I'm not going to have a go. So I want you to pause this now and actually draw it out. I'd rather you just pause it, do it, get it wrong, get it right, but I want you to try it. How would I go about drawing something that looks so complicated? What do I do? I would first, if I'm given the name, not given the structure, if I'm given the name of an organic compound, I would start from the bottom up. The bottom part is going to tell me my parent chain. And over here, it tells me my parent chain is a hexane. So it's going to be an alkane of some sort, the ane part there. and hexane, meaning it's going to be how many carbons? A parent chain containing 1, 2, 3, 4, 5, 6 hex. So I know that my parent chain is going to be 6 carbons. Brilliant. I've got like a third of it done. So now I need to figure out, how do I find this dichloro part? Like what do I do here? So it's dichloro is telling me there's 2 chlorines somewhere, and that somewhere is indicated by the number in front of the dichloro, and it's 2. So it tells me your dichloro, both of them are on the second carbon. Second carbon, eh? So left to right, right to left. When it comes to drawing, that's up to you. So I'm going to go from my right to left here. So on the second carbon, this is my first, my second, I'm going to place my 2 carbons like so. Great, 2/3 of it done. The last part then is 3 bromo. So it's telling me there's a bromo group on the 3rd carbon. So again, bromo up here, you can also put it down here, that's fine. I'm just choosing to put it up here. Perfect. So I've got my 2 dichloro and my 3 bromo, and now I just need to kind of throw all these H's on now to make up my 3 bromo, 2 dichlorohexane. Not bad. Now, to look at the other side of things, I need to stop sharing here. Go back to my OneNote. Yes, getting the hang of this now. So now I want to look at the other side of nomenclature, where I'm given the structure and I have to name it. So the first one, I see that I'm given a structure that contains this amount of carbons, this amount of special groups. Have a think. I want you to write it down, pause the video, write it, get it wrong, write it, get it right. I want you to try it. This first bad boy over here, what is the name of it? So again, just like we did before, we're going to seek out, the first thing we always do is we seek out the parent chain. The parent chain here is 1, 2, 3 carbons. 3 carbons will always, well, 3 saturated carbons as well. 3 saturated carbons will always indicate a what? It'll always indicate a propane. So it's going to be a propane. So I'll click your right propane down here. It's going to be a something something propane. And that pen is a bit too thick for my liking, but look, I'll keep going. Right, it's going to be some kind of a propane. So if I look around, is there any alkyl groups? Is there any halogens? Is there any etc, etc? So I see, yes, there is a halogen. There is a bromine group, and that bromine group is on the first carbon. You can write down 1 bromo, but again, the reason why I would be happy enough in this case to write bromopropane, torture. That's this bromopropane, all the one word there. So if it was on this carbon or if it was on this carbon, it would still be carbon number 1. You don't have to, you can write 1-bromo. You don't necessarily have to in this case. Okay, this suffices that it indicates exactly as unambiguous as possible bromine on the first carbon on a propane chain. Okay, the next one, I'm actually going to thin my the next one's a little bit more complicated, not too much though, just having a bit of a warm up here, guys. In this case, again, we see that we seek the parent chain. So in this case, the parent chain is 1, 2, 3, 4, 4 carbons. 4 carbons will indicate. I'll let you actually write this down in full as you see it. Give yourselves a moment. Pause it, just write it down. So I know in this case that because the parent chain is 4 carbons, it's going to be a butane. So it's going to be a something something butane. So butane. A good chunk of there done there. Now I need to have a look at what kind of groups do I have and where are they positioned. So I see that I've got a bromine on this carbon and I've got an iodine in this carbon. So I have to think about, first of all, how am I going to number the carbons? And the rule is, if you remember, have a think about it. What's the rule about numbering in carbons again? We want to get the lowest kind of numbering possible. So for example, if I decided I wanted to, let me just change the pen here. Let's say I wanted to number the carbons from right to left. I number it 1, 2, 3, 4. So if I numbered it like this, I would essentially have 1 bromo, 2 iodobutane. Okay. What would happen if I named it the other way? Or I numbered it, apologies, and numbered it the other way. So 1, 2, 3, 4. In this case, I would have 4 bromo, 3 iodobutane. So that's quite a higher order of numbers. You see, we've numbered the 4th and 3rd carbon if we did it from left to right. But if we did it on the first go from right to left, we would see that we'd have 1, 2 carbons. So it'd be much nicer, and that's just the rule as well. So 1, this is exactly what you want, the lowest numbering possible. So when we number them, we have to number them to get the lowest number possible. When we name them, it's always, 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 always alphabetical. So in this case, B before I, it's going to be 1 bromo, 1 dash bromo. You might as well write it down with me. Okay. Dash, apologies for this, 2 dash iodo. Dashes are very important. You will not get the marks, so you don't put them down. Iodo dash butane. So that's, so just to be really clear, 1 dash bromo dash 2 dash iodo dash butane. Okay, very, very important. Now, so that's kind of, I suppose, how you would number them and kind of name them. Now, moving on, I want to classify these bad boys. So moving on, we're going to look at the primary, secondary, and tertiary halogenalkanes. So what do we have here? We can classify our halogenalkanes. This is done according to the number of the alkyl groups attached to the carbon atom bonded to the halogen atom. Okay, so we're trying to look at the alkyl groups, are sort of which are always represented by our R. So if I can just, if we look at the first one here, it just depends how many of these R's, how many of these alkyl groups are attached to the carbon that's attached to the halogen. So in this case, we have just the one. We've got the one alkyl group, CH whatever, okay? The one alkyl group attached to the carbon, attached to halogen. This is what dictates a primary halogenalkane. In the case of a secondary alkane, okay, a secondary alkane will have 1, you guessed it, 2 alkyl groups attached to the carbon attached to that halogen, okay? So that's going to dictate, that's going to make our secondary halogenalkane. And lastly, this is going to be rocket science. We've got 1, 2, 3 alkyl groups attached to the carbon, attached to that halogen. That's what makes it tertiary. Interestingly enough, we don't necessarily need to know it for the spec. I like to dip into it and when we do mechanisms. Reactivity, how reactive they are. Funnily enough, the tertiary is more reactive than the secondary, and the secondary is actually more reactive than the primary, and it's all to do with the stability of this, is what we call a carbocation. But again, it's not in the spec, and I will go into detail about it later. This can be summarized in a nice little table where we can sort of integrate our nomenclature also. So again, we see here that the primary halogenalkane is where it has the one alkyl group, or i.e. that one R. The shortened formula RX, alkyl with the halogen. And if we look over here, we see that this halogen, our chlorine, is attached to this carbon, okay? It's attached to this carbon, okay? So how do we name this? So again, we have to identify the longest parent chain, which is 2 carbons, two carbons. Okay, don't mistake that for a methyl group. It ain't. Chains can be written like this all the time. This is a straight up parent chain right here. Okay, 2 carbons. It's also saturated. It's going to be an ethane. So how would I name this? How would I name this? Have a think. Is the chlorine on the first carbon or is it on the second? How do we think about this? So again, we want the lowest numbering possible. If we chose it from right to left, this is the first carbon. If we chose it from left to right, it'd be the second. We want to go with the lowest number possible. So this is going to be chloroethane. You can write 1 chloroethane, that's perfectly fine, but again, it's short enough and less complicated. We can call this chloroethane perfectly, or 1 chloroethane. Now, going down a wee bit, we see that the secondary, again, the number of alkyl groups is going to be 2, the shortened formula. So we've got our 2 alkyl groups attached to the carbon, attached to that halogen, okay? So in this case, we have the bromine attached to this carbon. And again, we want to try and name this, and we need to identify the parent chain. So the parent chain, again, is 1, 2, 3, or I guess 1, 2, and 3. Again, don't mistake either of these as a methyl group. This is a parent chain. Don't mistake it. So we see that this bromine, either way, it's going to be on the second carbon no matter what way you number it, because there's 3 there. 1, 2, 3, 1, 2, 3. So the bromine is on the second carbon. So we would call this 2-bromo, 1, 2, 3, propane. 2-bromo propane. The bromine's on the second carbon in a propane parent chain here. Okay, and the next one down, tertiary, 3 of those alkyl groups. It is denoted by this shortened formula R3, 3 alkyl groups attached to the carbon, attached to that halogen. Now in this case, we've got an iodine attached to this carbon. And if we wanted to name this, I will stay silent and I will get you to write it down. Have a think. Pause the video if you need to. Okay, so if we're going to identify the parent chain first, we could either go 1, 2, and 3, or 1, 2, and 3. Which way are we going to go? Either way, again, because of how, I suppose, just the structure of it, we can go 1, 2, 3 with a methyl group on the second carbon, or 1, 2, 3 with a methyl group on the second carbon. 1, 2, either way, we've got the methyl and the iodine on the second carbon, so this won't be too bad to name. Now, when we name it, it is still alphabetical. So numbering it, the halogens will actually take priority over the alkyl groups, just so you know. So in future, I'll probably give an example in another video. The halogens, when it comes to numbering, will take the priority. You want to number it nearest to the halogens than to the methyl group. But when we name it again, it will always be alphabetical. So I before M. So it's going to be 2-iodo, 2-methyl, 1, 2, pentene. Okay, 2-iodo, 2-methyl, pentane. 3 carbons, whenever you look at it, this way, it's still got a methyl and an iodine on the second carbon. Right, going a little bit more on the physical side of things, and this is actually evidence of what I have written down in my first video, but no worries. So solubility, so basically when we talk about solubility, we talk about how the ability of something to dissolve. So when we look at a halogenalkane, this X being the alkane, or the halogenalkane here, a halogen alkane actually isn't polar enough to make it soluble in water. So if you wanted to dissolve in water, or if a compound was able to dissolve in water, it would be forming hydrogen bonds. You need to form hydrogen bonds, I suppose, to dissolve in water. Thinking about hydrogen bonding, what elements are always involved in hydrogen bonding? Just a little recall there. Have a think. What elements are always formed in hydrogen bonding? Have a think and write it down. What elements are always formed in hydrogen bonding? I'll give you a hint. It's the most electronegative on the table, on the periodic table, I should say. So hydrogen will always be involved in hydrogen bonding. Hydrogen, oxygen, nitrogen, fluorine. Fluorine is the most electronegative element on the periodic table. So anyways, it's also important to note, I always like to mention, hydrogen bonding actually, I suppose, isn't a bond per se. It's an intermolecular force, just like the dipole and the van der Waal. It's a really, really strong intermolecular force. Not exactly correct to call it a bond, but it is, and that's what we have to deal with. But it is an intermolecular force. It's the strongest kind. We call it H bonding. So our halogen alkanes, they're not polar enough, they can't dissolve. So it's they're not soluble in water. The bonds that are just the intermolecular forces that do occur in halogen alkanes, however, are dipole and van der Waal forces, like I've written here. So dipole and van der Waal forces are the only intermolecular forces which occur in a halogen alkane. What is really good about halogen alkanes is that they are non-polar, and when it comes to dissolving and polarity, I always say like dissolves like. If I'm polar, I'll dissolve polar. If I'm non-polar, I'll dissolve in a non-polar. So halogen alkanes are really, really good for dissolving hydrocarbons, which are non-polar. Really, really good. They're great. They're actually used as solvents for it at times. What's really good about it, and a great everyday example, is we can use a dry cleaning agent. So what I mean by a dry cleaning agent, like not a washing machine where you require water. Dry cleaning agent, if I just had grease on my top right now, I could just spray this product called elbow grease, which is a kind of a halogen alkane halogen alkane based dry cleaning agents. I would just like give it a bit of a spray and it would actually take the grease off. So without the use of water, the grease, which is this kind of non-polar, just spray my non-polar halogen alkane based dry cleaning agent, it should come off. So that's pretty cool. That's the solubility there anyway. Moving on to boiling points, which would really get into the physical stuff. Wherever my thing is here. So when we talk about boiling points, so we kind of have to talk about trends when it comes to halogen alkanes. And one of them is boiling point. So the boiling point will increase down the table, down the group. It will increase down the group. Boiling point will rise and rise and rise and rise. Why is that? I would ask you, even though I've got points here, I'd still ask you to kind of formulate your own sentence, like why is that? What are the points there? What is it exactly? Well, we're going to use this image down here as well for reference. I wonder if I can just zoom out a little bit. So the reason why the boiling point increases is to do with the size of the atom, the bigger it gets. So when we go down on a group, we're adding more shells, okay? When we're adding more shells, the atom, look here, it's getting bigger and bigger and bigger. We add more shells, there's going to be more electrons, okay? When there's more electrons, there's going to be more van der Waal forces. So the more van der Waal forces, the more energy needed to overcome these weak forces, okay? So just like that GCA definition or GCSE definition, so the bigger the atom, okay, the more shells, the more electrons, the more van der Waals, the more van der Waals, the more energy needed to overcome these particular forces. Fairly simple, not fairly straightforward. Moving on from boiling point, I think that's all I wanted to talk about that anyway. I didn't decide here now. Yep. Fairly happy about that. Now, polarity, good old polarity. And again, I have evidence of my hard work from the last video. If I can just, actually, I'd rather get rid of this and write it as I go. So when we talk about polarity, what is the definition of polarity? Do you remember? What's polarity? For something to be polar, what's a polar bond? What is it? Well, to understand polarity, we have to understand electronegativity, which I'm sure everybody should, but either way, we'll pop over to this table here. So this is Linus Pauling. Linus Pauling is the guy that coined and sort of discovered the idea of electronegativity. So when we have a halogenalkane, we have a hydrocarbon, so we need to know our electronegativity value of a carbon, of a hydrogen, and those of the halogens. So thinking of electricity, electronegativity, looking at these values, how would you describe the trend of electronegativity of halogens? How would you describe it? So we see carbon is 2.5 there. The halogen is going to be attached to the carbon. It's decreasing, so we can, fluorine is the most electronegative element on the periodic table. So the most electronegative elements are going to be on the top right, and the lowest are going to be in the bottom left. So again, remember these guys involved in our hydrogen bonding as well. But yeah, so we see here fluorine, chlorine, big jumps down all the way down to, you don't need to know all that anyway, all the way down to iodine. We see that it's decreasing. Okay, so when we talk about electronegativity, that has a certain effect on a bond. So when our carbon is sharing a pair of electrons in a covalent bond with a halogen, the electrons in a covalent bond are held closer to the halogen atom. Why? It's more electronegative. It has a tendency to hug those, okay? It is way stronger. It really wants to, it has that force of attraction to hug this pair in this particular bond here. So that has a certain effect on the two elements in the group, okay? It polarizes it. This bond actually becomes polar, this unequal sharing of electrons due to the halogen being more electronegative than the carbon, causes the carbon to be a beautiful, very important definition. It allows it to be electron deficient, okay? Nearly takes the whole thing away from it. Electron, oh goodness gracious, come on. Deficient. I'm going to put electron diff just because it'll save us all the torture. So the carbon becomes a more electron deficient, and this in turn causes it to have a partial positive charge, delta plus, okay? And because this is hogging the electron, this is a very electron rich, that does not look like an R, that's supposed to be rich. This actually becomes slightly delta negative. So this opens up a bit of a path for our nucleophiles over here. So this polarity allows it to be involved in a range of reactions. So we have something called a nucleophile that you're all very familiar with. Our nucleophile has a lone pair it is dying to give away to that electron deficient carbon. Very nice guy. So a nucleophile, nucleus loving. The nucleophiles that we need to learn for AQA are the following. Can you name them without me even writing it down? So just to be clear, it's supposed to be an X there. These X's represent a lone pair. I know I have it like a circle up here, but hey, come on, we get it. So this is called ammonia, cyanide, hydroxide. Really important to note that nucleophiles don't have to have a charge. They don't at all. They have to have a lone pair of electrons. It's just that this is just the cyanide. It's just the way it is. It has a negative, has this gained pair of electrons here as a lone pair waiting to be given away, as does the hydroxide. The ammonia is completely neutral, but again, what these all have in common is they have a lone pair of electrons dying to give it away. So if I can do this, oh, giving away the secrets below. So if I change it to, I'm feeling red right now. So these lone pairs, so this lone pair and this lone pair of this nucleophile and this lone pair will just absolutely love to attack this electron deficient carbon. Would love to do that. Just go in there and give them some love. Nucleus loving, there they go. So the more, so again, talking about, I suppose, the trends, carbon to fluorine, very, very, very electronegative, huge difference there. Fluorine is really, really hogging the electrons in this case. And it is true to say that, I suppose, the more polar the bond, the more that electronegativity difference, the more likely that these, the more likely these nucleophiles will attack it. So the more polar, the more likely. So the more polar, the more electron deficient the carbon, the more likely for it to be attacked by these nucleophiles. Keeping that in mind, I'm going to pose a question to you. And that is true, like keeping it in mind, but it wouldn't be chemistry unless we had a bit of a, you know, unless we upset you a little bit. There we go. I want you to think about this question. So the more polar something is, the more likely a reaction is to happen. I suppose to rephrase it, the more polar something is, the more, I suppose, the polarity of a species allows it to be more reactive. So it's the fact that it's polar, the fact that the electronegative halogen is hogging all of the electrons, it wants them all, that's what dictates the reactivity of our halogenalkanes. Is that true? Is polarity, is that what it's all about? Is that what makes halogenalkanes more reactive? No. Even though we just discussed that fluorine is incredibly electronegative, we've seen here that yes, the nucleophiles are very likely to react the more polar something is. That is actually something else overrides that fact. Something else is, another factor is more important than polarity when it comes to dictating whether something's very reactive or not. What is it called? Very important. Can we think about it? Can you say it before I do? Bond enthalpy. Bond enthalpy is more influential, it's more important, it's a bigger deciding factor into why something is more reactive. What do I mean by bond enthalpy? Right. When I talk about bond enthalpy, I talk about how much energy is needed for a bond to break. Okay, how much energy is needed for a bond to break? That's what I mean about bond enthalpy. So we look at the trends here. Bond enthalpy. So the energy needed, bond enthalpy, the energy needed to break a carbon fluorine, carbon chlorine, carbon bromine, etc., decreases going down a group. Okay, it takes less and less and less energy to break off the iodine from a carbon than it would be to break off a fluorine from a carbon. And why is that? So again, if we look here, I have a carbon sharing a lone pair of electrons with the fluorine. It's actually down to its size, more or less. Fluorine is quite small. It is, yes, it is electronegative, but it's quite small. And the relationship between this lone pair and the fluorine's nucleus is quite strong. There's a huge attraction here between this lone pair and the nucleus residing in the fluorine. Huge. Fluorine's very small, it's going to grab onto it. So we see here attractive forces between the bonding pair being shared, and the nucleus of the fluorine atom is very strong as fluorine is very small. Exactly. The reason being as well, there isn't much shielding between the outer, there isn't much shielding between the outer electrons being shared and the nucleus of the fluorine. Okay, not much stopping those two trying to get as close to each other as possible. Conversely, and I'd like to look at this picture for reference as well. If you look at the bromine, it's a lot bigger. So again, it's really down to size here. Bromine's a lot bigger. It's got a lot more electrons, got a lot more shielding. So that relationship there between this lone pair and the nucleus within the bromine wouldn't be as strong as the fluorine because it's bigger. There's a lot more space, a lot more shielding going on. So better shielding, the shared pair in the bromine here, not feeling the attraction of the nucleus as much. So I suppose the attractive force here isn't as strong as it would be here. Very, very, very strong bond, would take an awful lot of energy to break, wouldn't take as much. And again, the trend we see here, fluorine and carbon, very strong. Chlorine getting a bit less, and then we see that iodine is probably has the weakest bond enthalpy. There's actually a bond enthalpy value somewhere. I should stick them up, but look, it's fine. So again, to put this into context, we've done this before. We've reacted our our Halogenalkanes in ethanol, and we've done the silver mirror test. When we get to precipitates, we know that the iodine or iodide actually precipitates the quickest. That reaction happens really, really fast. If there's an iodine on that carbon, more than likely the quicker reaction, the iodine will be more likely to break. So the bond enthalpy between the iodine and the carbon is a lot less than the carbon and the bromine, the carbon and the chlorine. The reason being the bond enthalpy is less. It's a bigger atom, okay? A lot more shielding, a lot less attraction between its bond pair and its nucleus on the inside, you know? So just to recap, and not to get these confused, going right back up to polarity again, right? So even though the polarity, the fact that, yes, fluorine is electronegative, so I suppose if we had a carbon and a fluorine, let's see if I can write it out, make more sense. Right, so the carbon and the fluorine, yes, the fluorine is way more electronegative. Yes, it has a tendency to grab on and hog electrons. But to be honest, that's not what's important here. What's important here is the amount of energy needed for the bonds to break. And in this case, yes, it's electronegative, but the enthalpy is so strong because of the size of the fluorine. And the bond, the enthalpy here is so weak because of the bromine. That's what really counts when it comes to reactivity. The fact that you can break this bond from the carbon a lot more easier is what dictates how reactive something is. So if I have a carbon with an iodine attached, it's going to be more reactive than if it had a bromine or a chlorine or any other of them, any else of them. Gosh, words. So again, it doesn't matter electronegativity. At the end of the day, the fact that fluorines have a tendency to hog more electrons does not dictate the reactivity of halogenalkanes. What dictates the reactivity of haloalkanes is the bond enthalpy, the amount of energy needed to break it, okay? Which is, I suppose, encompassed by the fact that the bigger the atom, the more likely it is to break off the carbon, okay? There's not much force there between the nucleus and the outer electrons, or the outer bond pair. But that's, I suppose, the main thing I want you to take from it. That's kind of the end of it here. But yeah, again, this is really is to just really understand that. But yeah, so what we might do is we might have a look at some MCQs and to see if we're really hitting home with this. So again, the electronegativity and the fact that you're hogging electrons does not matter. It doesn't make you more reactive when it comes to halogenalkanes anyway. The bond enthalpy does, okay? The bond enthalpy. The smaller their atom, the stronger that bond because of the lone pair electrons and the nucleus. I cannot stress that enough, people. Right, now, so I'm going to have to go straight on to my, so I'm going to do some MCQs here. I know I'm going to have to switch the page again, and this will take a few minutes. Not to share. Right. Oh, well done. I'm after giving away the answer. Great. Could be worse. Right. MCQs. Have a read, have a think, have a go. Which of the answers correctly describes the general formula for the Halogenalkane? A chéin a dó agus a trí, CnH2n plus 1, and the X to represent the Halogenalkane. It is not 2n plus 2. This, well, without the X, I suppose, blocking the X, this is an alkane. This is a Halogenalkane, all right? Don't put plus 2 here, it's plus 1. The halogen is going to replace one of those hydrogens. It is plus 1. Need to know that. Next one. Yes, this is a bit big. So the questions on the left, options on the right. Pause the video if you need to. You really, really evaluate the answers here. So looking at the table, we see that there is an increase in the boiling temperature. Correct. We also see that there is an increase in the chain length, sort of, as well as the different halogens. So what does that mean? So which of these statements best describes the trends that are apparent in the physical properties of the halogenalkanes? Pause the video if you need to. It takes much time. This is where you really condense your learning. So looking at the trend here, we see that there is a kind of a small halogen or small atom halogen, small chain. Small halogen atom, a little bit of a longer chain. Got a bigger halogen atom, methane chain. An even bigger chain and a bigger halogen. So what is going on here? So what's the most fair statement over here? Halogenalkanes increase in boiling point, yes, as the length of the carbon chain increases, correct. And the halogenalkanes increase in the boiling point when the halogen is further down. Why is that in group 7? So why is that again? Have a think if you can put it into a sentence why exactly that is. So the longer the chain, the more the van der Waals forces. But also the bigger the atom, so it gets bigger as you go down the group. You're adding another shell, you're adding more electrons, more van der Waals, more energy needed to overcome those forces. So it's going to increase, okay? Next one. Good old nomenclature. Have a pause, have a think, have a go. What's the IUPAC name? Hen, do, 3. 1,2-dibromopropane. Very simply, parent chain propane, but I suppose that's the only option they've given you. So it's a propane, and we see that on the first and the second carbon, we've got 2 bromines, so it's going to be dibromo. 1,2-dibromo, beautiful, simple enough. Now again, this is another one I want you to have a think about. Pause, have a think, have a go. Talk about nucleophiles. Rates of these reactions are affected by the electronegativity gap between the carbon and the halogen and the bond energy of the carbon-halogen bond. So which statement best describes the trends in bond strength and bond polarity in the carbon-halogen bond as you go down the group? Very important, don't get it mixed up. As you go down the group, what's happening? What's the fair statement? Really, you'll hit home now. Do we get this idea of enthalpy and polarity? 3, 2, 1. Fair statement, as you go down the group, the bond strength decreases, so that enthalpy, the amount of energy needed to break it, it gets less and less the further down you go. Okay, the bigger the atom, the less. Also, it is fair to say that the polarity also decreases. it gets less electronegative. If you look at iodine, the electronegativity difference between iodine and carbon is a lot less than fluorine and carbon. So it's also true to say, now not as you go down the group, but it's true to say as the bond strength increases, the polarity increases. That's also true to say. Cool. Next one. Have a pause, have a think, have a go. Haloethanes have the general formula C2H5X. Which statement best describes and explains the trend in the rate of reaction for the nucleophilic substitution of haloethane with the cyanide ion as the halogen being displaced goes down group 7? Okay. So yeah, I think so. Thinking of this X, so thinking of the halogens going down the group. So you know the order is fluorine, then replace it with a chlorine, then replace it with a bromine, then replace it with an iodine. What's the fairest way to describe this, or to use the statement and explain that sort of reaction, what's happening as you go down the group, what's happening? So as the rate of reaction increases because the carbon-halogen bond strength decreases, again, this is going back to the bond enthalpy. It's not polarity that determines the reactivity. No, 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 no. It is the bond strength, i.e. the bond enthalpy, how much energy is needed to break the bond. So we know as you go down the group, the enthalpy gets less and less and less. Atoms get bigger, the enthalpy gets less and less and less. Iodine is near the bottom. It's going to be the easiest to remove. It's going to be the easiest to react. Fluorine is going to be the toughest, okay, because of the size of it and the fact that there's a very strong relationship between its nucleus and those lone pairs, okay. I think this is the last one. Have a pause, have a read, have a go. So 3 halogenalkanes. So it's going back to that test tube. So you really need to know the colors. That's definitely on the spec. You need to know the colors. What are they? What's cream? What's white? What's yellow? So A is cream, B is white, C is yellow. Which one is the answer? Bromo is going to be the cream precipitate. Chloro or the chloride is going to be white, and iodide is always yellow. Okay. Thinking about which one is more reactive, how would you go about thinking about that? Which one is more reactive? So I think I demoed it. I'm pretty sure you must have done it once or twice. The iodo would always, or the iodide precipitate would happen first. It's the most reactive. Then it would be the bromo, and then the chloro would be significantly longer, again, because of the enthalpy. Okay, I'm really sure that's, yeah, those are for the next video. So that's it. I hope that it was of some help. I would really, really encourage you that after this video, you will go over, and again, I'm going to have to switch the old stop share. Yeah, so I want you to go to your OneNotes after we've done this. Do I even have your OneNotes up? Do I even have it as a shared screen? I should do. Bear with me. Is this it? Yes. Okay, sorry. So within your OneNotes, what I've done is you go to content library, click it opened, you go to classwork, and then under the 12th of May, Intro to Halogen. And what I'd like you to do is, if there's any questions at all, or you need me to elaborate even further, just ask me and I'll get back to you straight away. You can email me directly. You can write it down here. To be honest, it would be the quicker way. Completely anonymous. Just ask me. What's really important, if you just give me a bit of feedback for the session, was it helpful? How did you find it, etc. Again, it really need to see a bit more engagement between us. But hopefully that's of help. I'll be making, I'd say in a few hours, I'll be making videos on those mechanisms to help you. And again, I hope that was of some sort of a relief. Some kind of contact is nice. But yeah, no, but again, thanks again, and best of luck, guys. Oh, sign off way too slow with this. I can do this a bit more smoother. Okay, right. I'll see you again soon, guys.